Okay, I'm glad to have a chance to talk in this workshop. I want to talk with P1- and vertex-minors of trees and passes. We're going to work with Sang-Yeong. To define the vertex-minors and P1-minors, but in the last section, local complementation is defined already. You have a neighborhood of V and take edge complementation on the neighborhood of V. And another operation is pivoting on edge. If you have an edge UV in the graph, you find the set A and B and C such that A is the set of all vertices which are adjacent to U but not V, and B is the set of all vertices which are adjacent to V but not U, and C is the set of all vertices adjacent to both of them. And take edge complementation between the set A and B and B and C and the C and A, and you swap the vertex U and V. Also, it is defined by the terms of local complementation. You apply the local complementation U and V and U on G, then the result is exactly the same as this graph. You can check it. And vertex-minor is obtained from original graph by applying a sequence by local complementation and vertex deletions. And P1- over graph G is obtained from original graph by pivoting edges and vertex deletions. Also, in particular, two graph is pivot equivalent if you can obtain one graph from another graph by only applying pivoting edges. I note some important things. First thing is the P1- over one graph is also vertex-minor over graph, since pivoting on edge is defined by in terms of local complementation. So this is obvious. And also, hypertightness is closed on the P1-minor, since you think the definition of the pivoting on edge, then there are three sets A and B and C. But if a graph has a hypertight, then middle set is not appear. So if you take the pivoting on edge, also that middle set not appear. So hypertightness is closed on the P1-minor, but hypertightness is not closed on the vertex-minor. So P1-minor has some property. And actually, Joungkwon he generalized the pivoting on edge to some operation on matrix, and they have a result such that every pivoting sequence, you take every pivoting sequence can be another pivoting sequence such that every vertex in the graph has appear at most once in the sequence, and two sequences has the same result. You can change to it. I have an example for this situation. You have a graph G is the graph, and you pivot the edge AB and BC consecutively. And if you want pivot the AB, then the edge CD disappear, and you swap the B and A, and pivot the edge BC, then only swap the C and B. But this is actually same as G pivot AC. you pivot the AC, then BD disappear and the C and A swap. This graph is exactly same as the graph. Every pivoting sequence changes to something like this. And rank quiz and the linear rank quiz is defined in the last section, so I skip it. Our theorem is this. A graph G has a rank quiz at most 1. It is depend on if it is a vertex-minor over some path, some tree, and also G has a linear rank quiz at most 1. Then depend on if G is a vertex minor of some paths. And also, if G is bipartite, then this vertex minor can be replaced to pivot minor. So this is theorem, and also tree has a tree is at most 1, and the path has a path is at most 1. So this theorem says that there is some relation between length and the trees in terms of vertex minor or pivot minor. So I want to prove that I give a proof of the first thing, and we have time, then we briefly second thing. And I prove that graph G with rank is at most 1, it can be obtained from a vertex by a sequence of adding sequence such that pendant vertices or both twins and true twins. Twin means that two vertices have exactly the same neighborhood, and we call first twin if two vertices are not adjacent, and if otherwise we call them true twin. In fact, this class of graphs is called distance hereditary. Yeah. And actually we have a main lemma to give a proof, the theorem. Two graph H and G is a pivot equivalent, and H prime is obtained from H by adding one vertex of three types, pendant or fourth twin or true twin. You add a V or only one vertex. And then there is a graph G prime from G by adding a sequence of pendant vertices or pendant triangles such that G prime has a pivot minor isomorphic to H prime. Pendant triangles means that adding triangles such that the triangle has a common vertex, only one vertex of the original graph. We give that proof of the main lemma. This is what we want to prove. G has rank is at most 1, depending on if G is a vertex minor of a tree. But if look at the if part, since tree has a rank is at most 1, and if one graph is a vertex minor of that another graph T, then rank is at most of them. So if part is the obvious, we want to prove the only part of the theorems, and we suggest the proposition. If a graph G has a rank is at most 1, then G is a pivot minor of graph T without cycles of length and its full. And you imagine such a graph T, then every base is a triangle, and two triangles has no common vertices at least two, such like that. And if you add the vertices and one vertex on each basis and add edges from new vertices to vertices of triangles, and you delete the triangle, then you get some tree. And I claim that graph T is a vertex minor of this tree. And you simply do local complementation on vertex U and V, then you get this triangle and this triangle. So if you delete the vertex U and V, then you get the tree, the graph T. So this means that proposition implies a theorem. So I want to prove the proposition. Since G has we assume that G has a rank is at most 1, then by proposition there is some adding sequence, and with the last vertex of the sequence, then by induction G delta is also rank is at most 1. So there is a graph T without cycles of length and its full, such that graph T has a pivot minor isomorphic to G tilde V. So there is some pivoting sequence of pi in T and vertex K in VT, such that you operate the pi on T and delete K, then you get a graph isomorphic to G tilde V. And we want to add a vertex V with some adding a vertex or adding some graph in T. The V is one of the three types, pendant or false twin or true twin. In this picture, V is a true twin of W in G delete V. And since T cross pi and T cross pi, you delete the vertex set K in T cross pi, then you get a G delete V. So there is a vertex X corresponding to W in T cross pi, and you want to get a vertex V, so there must be exist a vertex Y in T cross pi. The T cross pi is a pivot equivalent to T, so in here we can use the lemma. By lemma, there is a sum graph T prime obtained from T by adding a pendant vertices or pendant triangles such that T prime has a isomorphic to pivot minor isomorphic to T cross pi. So therefore G is also isomorphic to a pivot minor of graph T prime. Because T prime has no cycles of length and is 4. You can check it. And this proves the proposition and also theorem. And actually lemma contains a killer of this proof. So I take one of the case of the lemma and I can prove it. The situation is this: H and G is pivot equivalent, and V is adding to H. Then let pi be the pivoting sequence, make G prime G to H, and we can assume that every vertex appears and most ones in pi by Gillen. We give a proof when X appears in a sequence pi. X can appear in pi or not, but we can choose that X appears in a sequence pi. So there is some Y such that XY is in the pivoting sequence, and if we pivot that edge, then we result graph is this. We want to make a true twin of X in the result graph. How do I get? You add the vertex B and C and make a triangle, and you do a pivot edge XY. Then in this picture, since B and C has adjacent to X but not Y, so B and C will be adjacent to all of the neighborhood of Y by definition of pivoting. So picture is look like this, and X, Y are swapped. Then X and B and C are all twins. You can see that all of the neighborhoods of X is same as neighborhood of B and C. So if you delete the X, you can replace to X, and C is a true twin of the B. So you make the true twin of the C. Remaining pivoting sequence does not change. The two vertices are true twins. So you get a theorem. And we give a linear length is one graph, linear graph. Can prove that also G has a linear length is at most 1 if and only if it is a thread graph. Thread graph is look like this. There is a thread blocks is connected by something like a path, and in the one thread block there is a vertex sequence, and there is a label. Each vertex has a label R or L or R and L, and edges are adjacent by this loop. For J is larger than I, then Vi is adjacent to Vj if and only if R is label in the Vi and L is the label of Vj. For example, V2 and you get the V2 and V4. V2 has a R and V4 has a L, so they are adjacent. And for example, V5 has R and V4 has L, but 5 is larger than 4, so they are not adjacent. This is a thread graph. Our theorem is that G of linear rank is at most 1, then depending on if G is a vertex minor of a path. Also, we want to prove that only part. Also, look at thread block. I make some paths like the graph, such that the vertex, every vertex has the number of vertices are n. Then we make the 2n minus 2 paths, and for each inner vertex, I mean not first and the last vertex, except the first and the last vertex, is corresponding to second edge and fourth edge and sixth edge and eighth edge. And we name the E2, E3, E4, and E5 and colored by red. And the V3 has label R and L. Then we make the new vertices and make a triangle with the E3. I claim that the thread block is a pivot minor of this something like path. You just do a pivoting consecutively, and you look at the E3. Then red is adjacent to left vertex of the E3, and the green vertex is both adjacent to vertices of E3, and the yellow is only adjacent to right vertex, so they are all adjacent with an edge, and you get a describe all of them. And then look at the E2 and E4. Then right vertex of the E2 is adjacent left of the vertex E4. This is exactly the rule of the vertex of the thread block. So if you can describe, you appropriately delete the vertices. If your V2 has a labeled R, then you delete the left vertex of the E2. And if, for example, V4 has a label L, then you delete the vertex, right vertex of the E4. Then you get a describe. Actually, you get the path has a vertex minor of this original path. So every thread block is a vertex minor of path. This is the all of the proof. And we actually can obtain a single result for rank is almost 2 or linear rank is almost 2. We have a catch up. Thank you for your attention.